Hey guys, welcome back. In this video we want to find the angle of twist at the free end of this shaft that's being applied, that has this torque applied to it. And you'll notice that the shaft here has two distinct cross-sectional areas. So the way that we do this is we use our angle of twist formula, which is equal to the sum here of all of the parts, and the parts are where any of these change. So we have TL over JG. And each of those has that little I there representing each of the parts. So if we look at this, we're saying that this whole thing is going to be made out of steel. So it will have a modulus of rigidity of 77 gigapascals. So that's constant throughout. The internal torque is going to be constant throughout. And the thing that's changing here is J, which is our each of the cross sections polar moments of inertia. So what we want to do, if we define this section, the little section as section 1 and the big section as section 2, then what we want to do is we want to figure out what J is for section 1 and also for section 2. So the formula that we use for the polar moment of inertia is just pi over 2 times C2 to the power of 4 minus C1 to the power of 4. Now that was from the previous videos, where C2 is basically the distance from the center, from the axis here out to this outer surface of the rod. And C1 was, if it's a hollow member, that's the distance to the inner surface. So this is a solid member, so C1 is actually just going to go to 0. So for J1 here we get pi over 2 times the radius, and the radius is 15 millimeters, but we want to write this in meters, so 0.015 meters to the power of 4, and that's going to give us 0.0795 times 10 to the minus 6 meters to the power of 4. Now we want to put it into units of 10 to the minus 6, because you'll see in a second when we plug it into this formula here that we're going to be able to cancel out a whole bunch of units, and it's going to be advantageous to us to have it in this 10 to the minus 6. For J2, we'll take the polar moment of inertia for section 2 here. We have pi over 2. Well, it's a solid member, so we know that C1 is going to be 0, so we'll have just the C2, which is the radius, so it's 30 millimeters, so we'll put that into meters, 0.03 meters to the power of 4, and that's going to give us 1.272 times 10 to the minus 6 meters to the power of 4. Alright, so now what we want to do is we want to plug these into our angle of twist equation. So we have our angle of twist, we'll do it by parts, so we'll do part 1 first. So we have 0.5 kilonewtons times the length of this section, which is 0.3 meters here. And this is all going to be over J here, so we have 0.0795 times 10 to the minus 6 meters to the power of 4 times our modulus of rigidity here, so times 77 gigapascals. Alright, cool. Now we'll add in section 2. So in section 2 we still have the same internal torque. We have 0.5 that was kilonewton meters, my bad. Kilonewton meters times the length here, which is 0.4 meters. And we'll throw this all over JG for section 2, so we get 1.272 times 10 to the minus 6 meters to the power of 4 times 77 gigapascals. Woohoo! Alright, so now if you remember from the last video, we showed that these units all count, if you write them exactly like this, so kilonewton meters times meters, divided by something times 10 to the minus 6 meters 4 times gigapascals, those actually all work out to canceling everything out, and you're just left with radians. So we can basically drop the 10 to the 6 meters 4, we can drop the gigapascals, and we can drop the kilonewton meters and meters. But only if it's written exactly like this. If we wrote this in newtons, then obviously this isn't going to work out. So if it's written with these units, we drop all that stuff, so we're just going to be left with 0.5 times 0.3. And then the bottom here, we're just left with 0.0795 times 77. Makes our lives really easy if we're using this 10 to the minus 6 and all these other units. So then this side here we have 0.5 times 0.4, and this was all over just what's left over, 1.272 times 77. So if we simplify this a little bit more, we're going to find out that this first term here is equal to 0.0245 radians, and this second term here just works out to 0.0020 radians. And if we just add those up together, we're going to find out that our angle of twist, let's write it here, angle of twist is just equal to 0.0265 radians. Alright, so that is the angle of twist at this free end. And if you're curious and you want to figure out what that is in degrees, well, all we have to do is we just multiply it by our factor here, 180. So we'll go times 180 degrees over pi radians. And this gives us the angle of twist at that free end there of 1.52 degrees, right? So that's 0.0265 times 180 divided by pi gives us 1.52 degrees.